Good morning, everyone. Myself, Shefali Varshney. I'm an assistant professor in HIT Department of CSC AIML. In this lecture, we will study about finite automata. Now, these are the topics that we will cover in this lecture. First, we will study about what is finite automata. Then, we will study the main parts of finite automata. After that, we will see what is DFA, that is a deterministic finite automata. Then we will see the transition function related to this deterministic finite automata. Later, we will see how does this finite automata work. Now, what is a finite automata? It is one of the most powerful models of computation. That means it is the most powerful machine in which we can give computation of any model, which are restricted models of actual computer. It is the most powerful model which are restricted model for an actual computer. Now these machines, in the last lectures we studied that automata is a machine. Now these machines are very similar to CPU of a computer. We can also say this machine as a CPU, the main working unit of a computer. They are restricted model as they lack memory, because since in computer we need a memory, similarly in a automata we also lack memory. In a finite automata we lack memory. Now finite automata is called finite because number of possible states and number of letters in alphabets are both finite. Number of possible states and number of alphabet are both finite in number. That means they are limited in number. And automata as well, because the change of state is totally governed by the input. That means if you are giving some input 0 and on 0 input the state A is going from, on 0 input it is going to B. If you will give input 1, suppose state A is remaining in state A only. That is the main difference. So finite automata is also called finite because there are limited number of states and alphabets in this automata. Now let's see the main parts of pictorial representation of this finite machine. Earlier we studied that it is a finite automata. Before that we can call it an abstract machine. So we can also call it a finite machine as well. Now let's see. After reading an input symbol, reading head moves one square to the right on input tape. What does this reading means? Suppose if you are giving some input 0, 1, 0, 0, there will be an input head that will be reading all these strings. So it is saying after reading an input symbol, suppose it has read this input symbol, the reading head moves from one square to the right of the input tape. So this will be your input tape. So that on next move, it will read the symbol in next tape square. Now, this process is repeated again and again until all the string members are being read by this input header of the string. Automation then indicates approval or disapproval. Suppose you are reading something, so there will be an end also to it. So it will be either accepting this string, either the machine will be accepting the string or it will be rejecting the string. If it winds up in one of the final states, the input string is considered to be accepted. It is saying if it winds up in a final state, suppose we are reading the string and this is your final state, that means your input header has reached this final state and this string is accepted. Or else the language accepted by the machine is set of strings it accepts, or else it will reject the string. Now let's see what is finite automata. Its goal is to act as a recognizer for specific language and pattern. As we can see, the main goal of finite automata, which is also finite machine, is to recognize a specific language or pattern. Now, what is a language? Suppose if a string is consisting of 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 1, 1. In this, we can see that the language has a pattern in which number of zeros and number of ones are equal. So this will be called a language. And there is a pattern in which number of zeros and number of ones are repeated equal number of times. Now we can see any problem can be presented in form of decidable problem. That means this can be a problem and we can represent it in the form of decidability. That can be answered by yes or no. That means whether this language is accepted or not. Now, hence this finite automata machine with limited memory can solve any problem. This finite automata machine can solve any problem. Now let's see, what is a DFA? DFA, the term itself defines, it is a deterministic finite automata. An informal definition is, we will further discuss the details in the further slides. Let's see the theoretical definition of this deterministic finite automata. A diagram with finite number of states represented by circles. That means there will be some states represented by circles. This diagram will be called a finite DFA, deterministic finite automata. An arrow points to one of the states, the unique start state. So the start state will be, there will be an arrow from the source coming from nowhere. This state will be your start state. And there will be a final state in which there will be two concentric circles. Double circles we can say. Now for every state, for every symbol in X, there is exactly one arrow labeled with that symbol going to another state. That means if this state is going from here to here, there will be an input symbol labeled on this arrow. Then and then only this diagram will be called a deterministic finite automata. Now let's see the formal definition of this. Deterministic finite automata DFA consists of these 5 tuples. Now these 5 tuples are Q, sigma, delta, Q and F. Now what is this capital Q? It is the set of states. That means all the number of states that we will be having in our transition diagram or in our DFA, those number of states will come under this Q. Now what is sigma? It is the set of input alphabets. That means on which the transitions are being performed. Now what is delta? Delta represents the set of transitions. What do you mean by this term transition? That means going through a change. That means you are going from one state to another. So that performance will be called a transition. And that transition will also be having an input. And that input will be called this input alphabet. Now this delta is represented by this symbol. And it represents the set of transitions that finite automata can take between its states. it is further defined by delta, that is q, into sigma, that gives a state q. That means a state from q set on giving an input alphabet will be giving us another state. Now, this is your transition function. It takes a state and input symbol as arguments. This is the further theoretical argument for this explanation. It takes a state, that is this. It takes an input symbol, that is this represented by sigma, and it goes to another state. It returns a single state. It returns a single state, which is defined by this transition function. Now, what is Q naught? Q naught is the set of start state or initial state. Q naught will be your set of start state or initial state. Now, what is F? F will be your final or accepting states. Now, these are the 5 tuples which we have in DFA. Now, let's see. What is a transition function? How does this transition works? Now, this is the further definition for transition. Delta gives Q into sigma, that gives another state, that is Q. Now, it maps from domain of states, letters, to range of states. Okay. So, this further diagram shows that a state Q naught on getting input alphabet A, it is going to Q1 state. This is the transition. And the state Q2 on getting input alphabet B is going to state Q2. So, this is how we define a transition function. Now, how does a finite automata work? Now, this is the loop. It reads a sequence of letters. Suppose this is a string. So, these are the letters it will be reading. Suppose this is a string A, B, A, B. So, it will be reading all these letters one by one until input string finishes. If current state is a final state, there can be a possibility where the starting state or initial state is a final state, then input string is accepted. Then we can say that this string or these strings are accepted. Else, the input string is not accepted. Then it will be not accepted. But how can finite automata be designed or represented? How we can show it? Now let's see. There are 2 ways to represent a finite automata. First is this transition diagram. Then we have the transition table. Now these are the transition diagram notations. If any state Q in capital Q is the starting state, then it is represented by the circle with arrow like this. This is your initial state and starting state. Now, how we can represent a final state? Now, nodes corresponding to accepting states are marked as by a double circle like this. We will make a double circle, then we will write the state within it. Now, this is the pictorial representation of a transition diagram. In this transition diagram, we can see we have an initial state, we have a final state, and we have this input alphabet on this arrow going from one state to another state. Now, it can be represented by directed and labeled graph, which is this. This is a directed graph, as we can see. Now, vertex is a state. So, this is a state. Now, starting and initial states denoted by circle and arrow. Final states denoted by 2 concentric circles, as we have seen in this diagram. Now, other states with circle. Simple, like this is another state. It is also represented by a circle. Now, transition function are the directed arrows connecting states. That means if this is a directed arrow, so this will be your transition of this state to this state. Now, let's see what is a transition table. In transition table, we will be having 2 columns. These 1 and 0 will be your inputs, and this will be your number of states. In transition table, you represent the states, initial state with this arrow, final state with a star. We will see on state A, when it is getting input 0, it is going to A. It is going to A itself. But when A state is getting an input 1, it is going to state B. Further, when state B is getting an input 0, it is going to state A. But when it is getting an input 1, it is going to state C. When this final state is getting an input 0, it is going to state C. And when it is getting input 1, it is going to state C. So this is how we draw a transition table. Now, let's see the acceptability of a string. That means when we will know that the string is accepted. A string is accepted by a transition diagram if there exists a path from initial to final state. That means if this is a diagram, so there should be a path from this initial state to this final state. Suppose this is the initial state, so there is a path. So this path shows that the string is accepted. There should be a path traversed that is equal to W. What is W here? It is the string. There should be a path for the particular string. Now, we should remember some particular points in designing a finite automata. First of all, we have to analyze the set of strings. Then we have to make sure every state is checked for output state and for every input symbol from a given set. No state must have two different outputs for single input symbol. That means from one state there should be only one output on a single input symbol. There can not be another transition on the same input symbol. If this is the case, then this will not come under the finite automata. There will be only one transition like this. This is a finite automata, and there must be one initial state, at least one final state in a finite automata as well. Now let's see an example. Now we have to construct a finite automata that accepts a string AAB over input alphabet A and B. Now we will simply draw these number of states. State S1 is going from S2 with A, S2 is going with A to S3, and S3 is going with B to S4. So S4 should be our final state and our initial state should be S1. So this is your transition diagram and this is your transition table. Now you have to fill this column on yourself like I have studied you in the previous slides. Suppose S1 is getting input A, it is going to S2. S1 is getting input symbol B, it is going to nowhere. So it will go to a state called trap state. So trap state is used when we have no use for any other input symbol and we have to show a transition for that particular state. In that case only we use this trap state, or we can call it a dead state as well. Thank you. So in this lecture we have covered finite automata, transition function, transition diagrams, transition table, the finite automata example, and in the next lecture we will further study about DFA and NFA. Thank you.